Welcome back to another edition of Math 30-2. I know that you've been excited and hyped for me to make more videos, so here I come with another Math 30-2 final exam review. Boom. We're going to learn Venn diagrams today. Oh, great start. Joking. Oh, a Venn diagram. A Venn diagram is a way of organizing our set information that we learned yesterday. Holy man, I'm still joking. So, if you think of a Venn diagram, it's always going to have a square. This square represents the universal set. Inside that square, there will be two circles. So there can be more than two circles, but typically there's only two or three. These circles represent the different groups that you have within that universal set. So you could have set A or group A. You could then have group B. And then you have the universal set. That's things that are on the outside that don't belong to either group. It's just a way of organizing info so you can quickly look at things. So for instance, if you look at this question right here, they want you to shade the Venn diagram and then list what's in that set. So the first question is just what's in group A? Well, if you look, this bubble right here is group A. I can quickly tell you that the numbers in group A are 3, 6, 9, 12, 15, and 18, as all those numbers are inside that blue bubble that I just circled. If I wanted to shade it on a Venn diagram, I would just shade that entire circle like that. The second question wants you to do group B, so that would be circle B. Here's circle B. It's pretty easy to tell. The numbers are 5, 10, and 15. Nice quick way to organize your data. If you were to shade it, you would just shade in that entire circle like that. If you look at the third one, that reads as A and B. So you're looking for numbers that are in both circle A and in circle B. The only number that's in A and B would be the number 15. If you were to shade the region A and B, it would be this region right here. There's no other spots that are in both circle A and circle B. Awesome. Do a couple more. If you read this one right here, this reads as not in A and in B. So you are looking for numbers that are not in group A and are in B. For instance, the number 5 and the number 10 are both not in group A and not in group B. And in group B. Some mistakes people make. Sometimes people think these outside numbers should also be a part of the set because they're not in A. While it's true that they're not in A, it says they and have to be in B. Those numbers would not count because they aren't in B. Another mistake sometimes people make is they would include the number 15. The number 15 would not work because 15 is in A, and the question said not in A. So if I was to shade this, the only regions I'm looking for is this region over here. That is the region that is not in A and is in B. Number 2. I'm looking for numbers that are not in A and not in B. So I'm looking for numbers that aren't in either spot. Good example of this would be these numbers on the outside. They are not in A and they are not in B. So my answer would be 1, 2, 4, 7, 8, 11, 13, 14, 16, 17, and 19. Those are the numbers that are not in A and not in B. If you were to shade it, we are shading everything around the outside of my circles in the universal set. Like that. The third one, always do inside the brackets first and then do not that. So the inside the brackets is A or B. If you think about this, that would be any number in A or any number in B. But then we want to not be that. So you're looking for the opposite of what I just shaded. Numbers that are not in A or B would be the outside, just like the question before. So even though these two sets might look completely different, they're actually the same result. So they're equivalent sets. Awesome. Reading Venn diagrams. So typically we use Venn diagrams, and you'll see them in the news and in business reports. If you go into business school or economic school, you'll probably do Venn diagrams because it's a great way to organize information from surveys and data. So this question talks about a Venn diagram of people who have pets, cholesterol issues, and are on a diet. So if you look, there's many questions we have that we need to answer. First question says, how many people only have pets? So that means you're looking for someone who has a pet but is not on a diet and does not have a cholesterol issue. This is my pet circle. The only people who have pets and not the other two would be these three people. Anybody else has one of the other two things. Right? So we're looking for only those three people. The next question removes the word only and says how many people have pets. Now I'm more inclusive. I'm including anybody that's in the pet circle. So for me, that would be 3 plus 1 plus 6 plus 1 for a total of 11 people that have pets in total. That word only is key. It changes how you approach it. Question number 3. It's asking for how many people have cholesterol issues and are on a diet. So cholesterol would be C, diet would be 2. You're looking for and. That means you need to be in both circles. A lot of people would answer 2. And while those two people certainly do have cholesterol issues and are on a diet, they're not the only people with cholesterol issues and on a diet. These 6 also have cholesterol issues and are on a diet. The difference between these two groups is the number 2 doesn't have a pet, the number 6 does have a pet. But this question never asked me anything about having pets. All it cared about was, do you have a cholesterol issue? Are you on a diet? So I would have to add those two together to find that there's 8 total people that have cholesterol issues and are on a diet. Number 4, how many people have cholesterol issues and are not on a diet? So now I want to find people who are in circle C but not in circle D. So for instance, these 68 people here have cholesterol issues and are not on a diet. These 2 people here have cholesterol issues but are on a diet, so we don't count them. These 6 people here have cholesterol issues but are on a diet, so we don't count them. And this one person over here is on a cholesterol issue and does not have a diet. Therefore, we need to include them. The difference between the 68 and the 1, again, is the pet. But this question never mentions pets. All it cared about was you have a cholesterol issue and you are not on a diet. Therefore, there's 69 people who have cholesterol issues and are not on a diet. Perfect. Number 5 and number 6. The number 5 and number 6 are good written response questions where you have to describe one of the numbers in the Venn diagram. The first one says, what does the number 2 outside of the circle mean? This number 2 right here. When describing something, make sure you mention all parts of the question. So the number 2 represents two people don't have a pet, don't have cholesterol problems, and don't have a diet. Notice that I mentioned all the facts of this question. This question mentioned pets, cholesterol issues, diet, and I had to explicitly say all three things. It does not have a pet, you do not have cholesterol issues, you do not have a diet. Mention all three things. For number 6, we're going to do the same thing. It says, what does the number 2 inside the circle mean? You need to mention all three things. It means that two people have cholesterol issues, have a diet, and do not have a pet. Right? Make sure you mention all three categories. You can't just be like, oh, it means that they don't have a pet. Or you can't say it doesn't mean, it means they have nothing. That doesn't answer enough. You have to have more detail, especially written response questions on diplomas and finals. All right, probability. Probability we do in this unit and in the next unit. So we'll do just basic probability pretty much today, and then we'll do a little bit harder stuff next unit. Probability of an outcome equals what you want to have happen divided by what's possible to happen. In Unit 1, our want and possible are typically pretty basic to find. So this says a fair die is rolled. What is the probability of rolling a 6? A fair die has 6 sides. And then I'm trying to roll a 6. I like to always break this down into what I want and what's possible. So the number of outcomes that I want to have happen, there's one thing I want to have happen. I want to roll 6. The number of possible things that could happen is 6. That means my probability is 1 divided by 6. Probabilities can also be represented as decimals. So if you go 1 divided by 6, it'll give you 0.16 repeated. Both those answers are the same, just represented in different ways. One's a fraction, one's a decimal. Question number 2. It says a card is drawn from a standard deck of cards. A standard deck of cards has 52 cards. What is the probability of drawing a heart or a club? A standard deck has 13 hearts, 13 clubs. So we always want to break these into what you want and what's possible. What you want any of the 13 hearts or any of the 13 clubs. You want 26 different cards. Any of those 26 would work. What's possible is that there's 52 cards in the deck, and you could possibly draw any of those 52, making your probability 26 out of 52. That likely would not be your answer on the test. If you put that in your calculator, it's 0.5. If you hit math frac in your calculator, it's 1 over 2. Those are your most likely answers. Awesome. Complementary events. We talked about complementary events yesterday. Remember, complementary events are opposites. So if you have complementary events, it would be like you roll a 2. A complement of roll 2 would be you do not roll a 2. Sometimes they can make it a little harder. So you could say like you roll an even number. And instead of saying you don't roll an even number, you say you roll an odd number. Those are complementary events. When you have complementary events with probability, their probability will always equal 1. Because they're opposite events, if you were to add them together, it should always equal 1 because 1 represents 100% of that happening. So if you had the probability of an event, we'll say probability of A, and you were to add the probability of its complement, so the probability of not A, it should always equal 1. It should be a guarantee that one of those two things happen. Sometimes we use that to our advantage, this idea that the probability of complements will equal 1, and we'll actually use that to our advantage in a couple of questions. Cool. Odds. Odds are also like probability in the sense that they're telling you the likelihood of an event happening. Right? And probability is a fraction way of representing something happening. Odds is more of a, what's the right word I'm looking for? It's more of a comparison of numbers rather than an actual fraction or a mathematical equation. So for instance, if we talked about the probability of rolling a 4, probability of rolling a 4 would be 1 divided by 6. There's 1 4 and there's 6 possible things. But if we talked about the odds for rolling a 4 or odds of rolling a 4, we actually represent it as 1 and then a colon and then 5. The reason we do it that way is probability is what you want divided by what's possible. Odds shows you what you want versus what you don't want. So when you're talking about rolling a 4, there's one number you want, there's 5 numbers you don't want. So it kind of gives you an idea of the likelihood of that thing happening. There's one thing I want, there's 5 things I don't want. When they say odds against, it just reverses the order. So now they write the don't want first, and they write the want second. Awesome. They write it out down here. Odds in favor is number of outcomes you want versus number against it. I don't really use those formulas. I used want versus don't want and don't want versus want. Cool. Mutually exclusive and independent events. So these are two definitions that sometimes get mixed up. Mutually exclusive is a term that you've heard before. Mutually exclusive gets used when we're talking about people dating each other. We'll say, oh, those two people are mutually exclusive. That means that they shouldn't date anybody else at the same time. This means in math that mutually exclusive means that the other events can't occur at the same time. So one thing happening means the other thing can't be happening. Independent events mean that two events affect each other's probability. So if you're independent, you do not affect the other thing from happening. For instance, let's take two events like me waking up before 8 a.m. and it raining outside. It is very possible that I could wake up before 8 a.m. and it's raining outside. Therefore, those events would not be mutually exclusive because it's possible they both happen at the same time. These events also are independent events because me waking up in the morning before 8 a.m. does not affect the probability of it raining outside. Although that'd be kind of cool if my wake up time affected the time it rains, but it doesn't. So these are independent events because my waking up does not affect the probability of it raining. In math, we have a bunch of formulas. Just the formulas are provided to you. So on your formula sheet, you will see these things, but you won't know which one's which. It's up to you to remember which one's which. They do appear in this order on your formula sheet, I believe. The first one is your mutually exclusive formula. So if two events are mutually exclusive, you can add together their probabilities and it'll tell you the probability of A or B. If two events are not mutually exclusive, you then have to subtract the probability that both of them happened. Dependent formula gives you a new symbol that we haven't seen before. So this one, well, I say we haven't seen before. We haven't seen it in a long time. This reads the probability, so this B stands for probability, that event B occurs. And then this bar means given that. A has already occurred. So if you were to read this, that's the probability of B given A happened. Where we saw this was like when we would draw cards from a deck and we would do it multiple times. Remember, we would do questions like that? I'd be like, okay, you draw a card, it's a heart. What's the probability of drawing another heart? Well, now, because the first event happened, my second event changes its probability because there's less hearts in the deck. The last formula that they have down there is your independent formula. Basically, you get that the probability of A and B is equal to probability of A times probability of B. Awesome. At the end of the day, the biggest thing that I usually tend to rely on is when I look at these formulas. This formula is for words like or. Right? This is or. So or means add. So when I see the term or, that tells me I should be adding my results together. The second big thing I do is I see this one is for the word and. And means that you should multiply. Now, that is like a general rule of thumb. It won't always work perfectly, but it will work enough that it'll bail you out if you ever need it to. The word or means add your probabilities. The word and means multiply your probabilities. Awesome. We have one question here, and then we'll be done. So we have the probability that Shaw will pass math this semester is 0.7. The probability that she will pass English is 0.9. If these events are independent, determine the probability she will pass math and English. And means multiply. Also, they told me it's independent. So if I look up here, I notice my independent formula, which is probability of A and B equals the probability of A times B. So if I want to figure out the probability that she'll pass math and English, probability of math and English, then that is equal to the probability of math times the probability of English. That means if I want to calculate this, I go probability of math with 0.7 times the probability of English, which is 0.9. That will give me 0.63. That is the probability that I pass math and I pass English. Awesome. B. B is the probability that you pass math or pass English. Now, or means add, but we have to ask ourselves, are these mutually exclusive adding or not mutually exclusive adding? Mutually exclusive means the two things can't happen at the same time. Is it possible that I would pass math and pass English at the same time? And the answer is definitely yes. Like, it's possible Miss Schaub could pass both classes. Therefore, we need to use the non-mutually exclusive formula, which is that the probability of math or English equals the probability of math plus the probability of English, which is what I was saying. Probability of or is always adding. But then we need to subtract the probability of both. Like that. Because this is non-mutually exclusive, I need to use that formula. That means I need to do 0.7, because that's the probability of math, plus 0.9, that's the probability of English, minus 0.63, because that's the probability of math and English, which I just figured out over here. If you put that in your calculator, you get 0.97. Which makes sense. Is very close to 1. 1 means it's 100% chance sure that's going to happen. Now, that makes sense because the probability that Miss Schaub just passed English was 0.9. So that's a pretty good chance. The probability she passes math is 0.7. That's also a decent chance. So the probability that at least one of them passes should be very good. Awesome. The last one. This is the probability of math, but not English. The word but sometimes throws people off. It means the same thing as and. So this is like saying the probability of math and not English. To figure that out, we would have to do the probability of math times the probability of not English. We know the probability of math, so we can do that part. It's 0.7. What we don't know is the probability of not English, of failing English. To figure that out, we need to use the idea of a complement. Complement is opposite. So if the probability that I pass English is 0.9, the probability that it's not English would be 1 minus 0.9 to give you 0.1. The reason why it's 1 minus is because 1 represents 100% happening. We subtract the probability of what the opposite is, which is passing English, and that will leave me with the complement, which is not passing English. If you multiply those two numbers together, the probability of passing math and not passing English would be 0.07. A very small number, which makes sense because it's very unlikely that I fail English or Miss Schaub fails Miss English. Wonderful. There's a question here. If you want, you can go ahead and try it on your own. So maybe pause the video, try it on your own, and then unpause and see how you did. All right. So hopefully you paused the video and tried this question. It says, in a group of students, the probability that a student chosen at random walks to school is 0.35, and the probability that a student has blonde hair is 0.2. If the probability that a student has blonde hair or walks to school is 0.45, calculate the probability that a student has blonde hair and walks to school. Okay. Blonde hair and walks to school. We have two choices here. Choice number 1 is to use this formula for P, A, and B, or this formula for P, A, and B. One of them is the dependent formula. One of them is the independent formula. Independent means that the two events would not affect each other's probability. Normally, this question would tell you for sure whether things were independent or not. Now, logically, blonde hair walking to school should be independent of each other. Your hair color shouldn't make a difference if you walk or not. But maybe in some crazy world, it actually does affect each other. So because we don't know whether or not it's independent or dependent, we don't know which one of these formulas to use. But What we do know is that we have some other information for once. We have the probability of walking is 0.35. We have the probability of blonde hair is 0.2. And then we also have the probability of blonde hair or walking is 0.45. Now, if these events were mutually exclusive, then adding those two numbers together, the probability of walking plus the probability of blonde hair, should equal the probability of walking or blonde hair. But it doesn't. If you were to try the formula, you would get 0.45, that's the probability of walking or blonde hair, equals 0.35 plus 0.2, and it doesn't work out. The reason it doesn't work out is because these events are not mutually exclusive, which means you need to do this part of the formula, which will be our probability of walking and blonde hair. And we can use this non-mutually exclusive formula to find what we want, which is the probability of walking and blonde hair. The way you're going to do that is you're going to subtract these numbers to the other side. When you do that, you end up getting, it's going to be a negative number. You end up getting negative 0.1 equals negative probability of walking and blonde hair. Those negatives cancel each other out. That means it's 0.1 is the probability of walking and having blonde hair. We could not use the independent formula or the dependent formula because we never got told if the events were independent or not. Question B, the probability that a student has blonde hair given they walk to school. Okay. Blonde hair given they walk to school. That's written like this. The probability of blonde hair given they walk to school. That's what that means. There's only one spot that we see that formula. We see that formula right here. I'm going to highlight it in yellow. It's the only time we ever see that bar. You can rearrange that formula by dividing both sides by the probability of what's happened. So if I divide that to the other side, and that's the probability of what has happened, then that will cancel out and I will have a new formula. And that formula would be the probability of A and B divided by the probability of what's happened, which in this case is A, would equal the probability of B given A. This formula, which we just created, can then be applied to our question. The probability of blonde given you walk would be the probability of blonde and walking divided by the probability of what's happened, which is walking. That's what we were given. That means if you throw this in your calculator, 0.1 is the probability of blonde and walking divided by 0.35, which is the probability of walking. You go 0.1 divided by 0.35, and you get the probability of blonde given that you walk is 2.9 when you round it. Awesome. That last question is on the harder end. Like, that's a hard question. You probably won't have to do something like that. But this is not that hard. Like, that's something you will probably have to be able to do. So if you're just thinking about studying and what to worry about, what to panic about. Awesome. We're going to stop there today. We'll come back and we'll start Unit 2 tomorrow. Take care.